square roots, an overwhelmingly common mathematical operation that, as it turns out, is a little bit hard to actually do or implement programmatically. We've seen a hint of this previously when we looked at the fast inverse square root function. We saw that was actually implemented in the Quick engine, and it used a bunch of hacks to achieve this. We concluded then that there wasn't really a straightforward way to, achieve the correct result for a square root, and so we had to use some form of approximation. Today, we're going to take a look at an approximation technique that was used in that algorithm at the very end, and we'll see how we can build a square root function using just that. You're watching a Random Wednesday episode on 0612 TV. Hello and welcome back to another Random Wednesday episode. Now, to start off with, I have to tell you that the first half of this video, give or take, is kinda messy. Yes, we will be looking into the math behind this method, which, is known as Newton's method. But ultimately, this is still a programming/computing kind of tutorial. So our goal at the end of the day, despite all the math, is to be able to build a function that can help us approximate square roots to, a level of error we want. So yeah, with that, we can have a quick overview of the entire video. Now, this video comes to you in two parts. The first half will be, as I've said, pretty mathsy. We'll try to understand square roots, a little bit deeper, and try to understand how Newton's method actually works. What is its approach to approximating a square root, and how we can actually do so very well. With this in mind, in our second half, we'll shift over to writing some code. Essentially, we'll be implementing what we've discussed before, and we'll see how we can basically, get it to give us pretty good answers for our square root operation. So with that in mind, let us jump into our first part where we take a look at the math. Here's the deal. At the end of the day, we want to get the square root of a number. Let's keep things simple. Let's say the number is 9. So we'll use 9 throughout, right? And when we sort of have an idea of where we're going with this, we'll replace this with an unknown to make it, more general, more dynamic. Now, let the answer we're looking for be x. So x is the square root of 9. We can then tweak this up. Essentially, that is equivalent to x squared equals to 9. And if we rearrange the equation, we end up with a quadratic equation. Getting things in this form is important, because then what we can do is we can actually, think of it as a function. We could plot it out. And essentially, the roots of the function would be the square roots of the number we're actually looking for. In this case, if we were to just plot out this graph, you will see that we have an intersection here at position 3. That is the answer, right? Square root of 9 is 3. So what we've just done is we've taken a basic square root operation and we've sort of pushed and prodded until it became a function. And once we have things in this form, we can start to apply Newton's method to it. Here's the deal. Newton's method allows you to make an approximation for the roots of an equation by essentially letting you guess. You make a guess, right? It doesn't have to be accurate at all. But what you can do is you can look for the tangent line at the point. That is a straight line describing the curvature of that part of the line, right? You have that line, draw it out, extend it until it cuts the x-axis. That point of intersection will be closer to the roots than your previous guess. You can use that x value to be your new guess and repeat this process. Every time you do this, every time you draw out that tangent line and let it intersect the x-axis, you get closer and closer to the actual root. That is the idea. Now, the good thing about what we've just done is, we have the function itself already. All we have to do next is to just make a guess. Once we've made a guess, we need to find the tangent at that point. This is where things get a little bit more complex, because essentially to get the tangent, you must know the gradient at the point, right? That is, of course, the slope of the current position. And in order to do that, you have to differentiate your original equation. Now, I get it, calculus is scary, but this is just a simple quadratic equation with a constant term at the back. So, hopefully the differentiation isn't too difficult. Essentially, you just end up with 2x and you discard the constant term. So yeah, that should be fine, right? Now, turns out that derivative will give us the gradient of the tangent line, which is something that's very important to us. In fact, with this gradient, we are on our way to actually drawing out our tangent line. Before we go on, let's give a value to the guess that we've made up to this point. Let's say our guess was 4. Given the derivative we have here, right, plugging in the number 4, that tells us that the slope, the gradient of our tangent line, must be 8. This puts us on our way to drawing our tangent line. But if we just say y equals to 8x, that is going to be, well, aligned with the correct gradient, but positioned wrongly. That is the green line in this picture, and as you can see, it's sort of just hanging out in the middle. We want to actually get it to stick to, our actual guess point on the line, right? So we need to do some things to push this in position. First, let's push it towards the right by subtracting a value from x. That's just how graphs work. You want to push it forwards by 4 positions, you have to subtract by 4. You can think of this as essentially delaying the 0 point of this line. The reason why we use 4 and not any other number is because that is our guess. We guessed 4, right? So obviously, the gradient that we're looking at must be at position x equals to 4. So we push it to the right. It's still not aligned to the actual line itself, and that's not surprising because we need to push it up as well. But the question is, how far up? Luckily, that's not too difficult. It needs to go just far enough to touch the line. And we happen to know the equation of the line, right? It's simply this. So we substitute the value of 4 in here. This gives us a vertical bias of 7, right? We've integrated that into our equation as well. And as you can see, this line touches my main equation line perfectly. And it gives us the tangent line at that point of intersection. But the thing is, why go to all this trouble? Why do we need the equation of this line? You see, we need this because ultimately, we are trying to find that point of intersection. That point in which the tangent line actually cuts our x-axis. With the equation, finding this point of intersection is extremely easy. Because, well, if we know that this is the equation, we essentially want to find, the value of x when the value of y is 0, right? That's essentially what's happening here. This point has an unknown x, but a known y, and that is 0. So all we need to do is to substitute 0 for the y. This gives us an equation in which we can solve for x. At the end of the day, we get a new guess. X equals to 3.125, which, of course, is a much closer value than 4. Of course, we know the actual root is 3, right? So this one is definitely a far better answer than 4. Of course, if this looks like a lot of steps to you, I don't blame you. We clearly don't want to sort of start here, right, and go through all the work just to get one guess. Luckily, as it turns out, we don't have to. This process is essentially the same no matter what value you give it. To see this, we can represent our equation in a general form. This is as general as it gets. If we don't think of our functions, in terms of their actual values, we can think of them as just a function f. So you can actually use this to approximate many types of functions, and as it turns out, the overall form of this is exactly the same. Remember, this is just our tangent line equation, so the 3 parts we've just looked at are still there, right? Firstly, our gradient is here. This is of course just the derivative or the differentiated version of the original function. This is still here. We have our x bias right here, as well as our y bias, which taps upon the function itself. So this is just the generalized form of the equation. Now remember, we want to find the x-intercept, so we simply substitute 0 here. We get this, and essentially what we can do is we can rearrange our equation so that it looks something like this. Our next guess is simply our current guess, used in a formula like this. Of course, this is a very general form, and in fact this is sort of, the one-liner definition of Newton's method in a nutshell, but this entire thing is supposed to boil down to square roots, right? So let's bring it back to talk about square roots itself. Now, we have things expressed in terms of fx and f prime x, and remember, in the context of square roots, it is simply these two equations. Now, previously, we have our value fixed in 9, right? So whatever we do, we end up looking for the root of 9. Let's make this a little bit more flexible by changing that to I instead. Now, whatever value you plug in for I, we'll be finding the roots for that number. So this is the general form of our two equations. Since this is what Newton's method says we need to do, then we can simply substitute these two things in, and we will end up with a version of Newton's method that we have basically customized for finding square roots. That, as it turns out, looks something like this. Xn again refers to my current guess. Xn plus 1 will be our next or improved guess. We've substituted f and f prime x over here. So yeah, we can substitute our current guess in these three places. That gives us a better guess which we can plug back in. That gives us an even better guess, and so on. We can basically do this iteratively, and yeah, we'll get better and better results. Obviously, we've got to stop somewhere. So yeah, that is a decision we have to make when it comes to our programming stage. So hopefully the ideas here aren't too difficult to understand, right? At the end of the day, all we're doing is we're just trying to, well, get closer and closer to the original root by drawing out a tangent line from our current guess. With this in mind, we can move on to our code. As it turns out, the coding part is pretty simple because, well, we just take what we've just done, right, which is already a step-by-step algorithm, and we just turn it into code. Simple as that. So we're going to be doing today's exercise in Python, and yeah, we'll see. It's not too difficult. Let us build an approx square root function. It takes in a number, and it's going to give you an approximate square root. Essentially, we need to run Newton's method over and over again until, well, we get a close enough square root, right? We get a, square root value that is within a certain amount of error. Now, there are many ways of approaching this, right? But what I'm going to do is I'm going to just, well, set an error parameter here. The idea is that if between iterations we get a difference that is less than a certain amount, we'll consider it good enough. There are pros and cons to using this method, right? And there are of course other methods as well, but we'll stick with this since this one is fairly easy to understand. We'll actually give this a default value. Let's keep this small, and let's say, well, we want 5 decimal places of precision. As long as the error is smaller than this amount, it'll be okay. Of course, this being a parameter, this can be overridden by a user if required. So essentially, we start to guess. Now, our first guess is also something that isn't, cast in stone. If you cast your mind back to the fast inverse square root function, they use a pretty hacky method to find, well, essentially a first guess, which is considered very much good enough. In our case, we're not going to do that. Instead, we're going to start off our guess at just the value that was given. Clearly, that's a horrible guess, but you'll find that, well, using Newton's method, we'll zoom in on a correct answer pretty quick. We will also calculate a difference. Now, this difference is essentially what we're going to be using to match against this error we have up here. Right now, let's just make the difference a very big number. Then we can say, well, the difference is greater than, the error that we've set here, right? We'll keep going. We of course need a loop, right? So we can keep iteratively improving our guess until it basically meets the level of error that we're okay with. With this, we can immediately implement Newton's method. So the new guess is simply the existing guess, subtract guess square minus, the value that you're actually looking for, right? The original value that you want to take the root of. Then divide by the derivative, right? So in this case, it will be 2 times the guess. So yeah, this is Newton's method in one line. In fact, this is all of Newton's method. Everything else is just there to support this. Anyway, we have this, right? And what we can do is we can calculate the error. So the diff here, right, is essentially the new guess minus the previous guess. Now, here's the deal. This number could be positive, could be negative, right? Because of course, when you're actually doing the approximation, you could overshoot to the other side. We're not sure which one of these numbers are actually bigger. So essentially, we want to take an absolute of the difference, right? The error is always just the magnitude. One way you can do this is to use an absolute function from the math library. But if you don't want to do that, you can also use an if statement. So if diff is less than 0, diff times equals to 1. Negative 1. So what you're trying to say here is if that error there is negative, we'll multiply it by negative 1, hence flipping it to a positive number. When we get past this point, our error is definitely positive. We only have one more step to do, right? And that is in order to actually forward our guesses correctly, we say guess equals to new guess, like so. How this is going to work then is that this is going to keep running. It's going to keep generating new and far improved guesses. Each time we get a guess, we check and see how much difference there actually was. Then we update our guess to the new guess. We'll loop around here and we'll check to see if the difference is actually greater than the error. The idea is that if the difference is still too big, right, in other words bigger than this value or whatever value that was supplied here, we'll continue through the loop to refine our guess. Otherwise, well, we're basically done, right? And we can just jump out. And when we're out, we can simply return our guess. And this is, considered as good of a guess as we can make. Let us now try and run our function. Let's print out the, approximate square root of 9, right, since that was the example we were using. We run this and the answer we get is 3. It's exactly the result we're looking for, which is of course great. Let's try a bigger number and see, what happens to it. Right, 1024. When we run this, we get 32 points, a bunch of zeros and then an 8 at the back. This is considered a pretty good approximation. And yeah, given the amount of error we've set, this is fine, right? Of course, the actual value is 32. If we try and look for a number that cannot be rooted, let's go for a random one, 427. Let's see what happens. Well, when we run this, we get an answer, right? But we have no clue how close this answer actually is. So what I'm going to do is I'm going to come up here, I'm going to import math, and I'm just going to check this value against the actual, answer that you're going to get. So using Python's actual square root function, which I'm going to just assume is ground truth, let's compare up these two values and, whoa, they actually look exactly the same. I'm guessing this is somewhat coincidental, since of course we didn't ask for this many decimal places worth of precision, right? But things seem to be fairly okay. While we are on this subject, we can of course take a look at how we can adjust up the error, right? If I want the error to be smaller here, then we'll get a slightly less precise answer. You'll see based on what we have that, the answer is still pretty close. What we can do is we can quickly assess, how much work this actually requires, since this is an iterative process. It of course takes some time. And how we can do that is we can maintain a count. Essentially, let's start off with 0 here, right? And every iteration will increase the count by 1. Then at the end of the day, what we can do is, let's just print it out, right? Print approximation in this number of guesses. So what I'm doing here is I'm just trying to show the count on screen. For grammar, let's fix this real quick. So for that value, we took 8 guesses. Not a great number, but our CPUs are fairly fast, so that shouldn't be an issue. Of course, if we want things to a greater level of precision, right, let's throw in more zeros. Then, of course, we take more guesses, though in this case, it's just 1 more guess. We can also force this to be, a lot more precise. I don't know how, that's still 9 guesses, right? So, not too bad. You get the idea. This is a very simple way in which we can do a square root approximation using Newton's method. This piece of code will be available in the video description. I'll of course annotate this with a bit more comments to make this, a little bit more readable for you. But essentially that's as simple as it gets. I'll also upload a different piece of code that is interactive and gives you a little bit more analytics, I guess, to sort of show you in better terms how the approximation actually sort of refines itself over the iterations. Both of these downloads can be found in the video description, so do pop it open and take a look. And there you have it. You have just written a square root function that, can give you an approximation to a certain number of decimal places. So like we were talking about in the fast inverse square root video, we've never really given the procedure to, get a square root any thought. Usually if we have to square root a number by hand, it's a number that, we are already very familiar with. But the truth is, we could square root any old number, and well, usually we just go to a calculator. We never really have a chance to think about the actual implementation of this. And well, now that we've seen this, hopefully we can have a better appreciation of what our devices are doing to give us the answer. Obviously, most devices are not going to go through such a long iterative process. They may have some other way to make things, a little bit faster. But yeah, if you wanted to figure out, the answer to this, Newton's method is a method you could use. And we've just seen the code to make that happen. That's all there is for this episode. Thank you very much for watching. I hope you've gained some insight today. But until next time, you're watching 0612 TV with NERDfirst.net. Thank you very much for watching. If you like my work and are feeling generous, you can shoot me a one-time donation on PayPal or sign up for a recurring one on Patreon. Of course, you can simply like, comment, and subscribe. You know the deal. For more videos, links to my channel and a related playlist are on screen. Thank you for your support.